Okay. So till the previous session, I have demonstrated in the previous two sessions, 2 Sundays. Uh, I have demonstrated how to make maps using GIS. Now that was basically like taking ingredients and cooking something, cooking a map with clear instructions about what to do. It was just a demonstration. We are going to learn about the how-tos, about actual how-tos about it a little later. But before that, we have to learn the fundamentals of geography a little and fundamentals of GIS or whatever is relevant to GIS. That is important. Now, why it is important? I'll tell you before I proceed. I'll tell you a small story. One of my close friends, his grandfather had a harmonium making factory in Delhi, and his father also used to be a very good harmonium player. So once someone came to his father and asked him, "Can you teach me harmonium?" He said, "Yes, you are welcome. I'll teach you free." So he came, and then the next day, the first lesson was Sa Re Ga Ma. Then the person said, "No, no, I don't want all that Saregama or whatever. You just teach me a few Hindi movie songs and I'll play them." He said, "No, it's not like that. If I teach you just a few Hindi movie songs, then you'll always only play them. You will not know how to play new songs yourself." So what I'm telling you is precisely like this. Today I'm going to whatever I had shown yesterday in this previous session demonstration, and maybe some things that going to demonstrate in later sessions also. Later sessions, I'm going to tell you in later sessions also, uh, they are actually they are actually like Hindi movie songs, which I'm just telling you how to play. But if you learn only that, you will not be able to create your own fresh maps and your own maps from scratch and maps which are accurate. So, in order to have good, accurate maps and be able to do any kind of mapping, you need to learn the fundamentals. So, that is where we are. Now, what are the fundamentals? Where do we start? In the fundamentals of the GIS or the fundamentals of geography, rather, the first thing that comes to our mind is the shape of the earth. So I'm going to today go in detail about what is the shape of the earth. Now you are seeing a lot of items behind. All those will be used. You are seeing different fruits with different shapes. All those will be actually used to demonstrate. So I'm going to first demonstrate by just talking like this, and then I'm going to start the presentation. So what is the shape of the earth? So like almost everyone, most of us know that the shape of the earth is spherical. Uh, but when we talk about any shape or anything rather, it depends the shape or the appearance, whatever we are seeing, it depends on how closely we are looking at it. If we look at something from far away, it will look something like this. But when we come very close and start microscopically examining it, then we might see some differences. It may be a perfect sphere right up to whatever, or it may not be a perfect sphere. So the first possibility or the first best possibility that the earth is a perfect sphere. Now this is a sphere, meaning this is nothing is perfect, so this will also not be 100% perfect sphere, but let's call it. So this is a ball which is a sphere, which is a perfect sphere. So the earth is like a perfect sphere. But then most of us would have learned in school also or heard that it is not a perfect sphere. Earth is not a perfect sphere. It is oblong, or they say it is. I just forgot the word. It is collapsed, slightly depressed. So whatever, oblong, depressed. So it is like what? Not like a sphere. Then what? It's actually like an ellipsoid. So what is an ellipsoid? People who might have heard the word for the for the first time. So you almost all of you know the circle and an ellipse. In two dimension, circle is a perfect circle. Ellipse is oblong, and circle is also an ellipse, meaning circle is a special case of an ellipse where both the diameters are same. In ellipse, we have two diameters, major diameter and minor diameter. So ellipse is a longish circle. Same way, in 3 dimensions, the equivalent of a sphere is an ellipsoid, which means a oblong sphere, which is slightly longish. So, okay, we get it till then. So Earth is not a perfect sphere, but Earth is an ellipsoid. So what kind of an ellipsoid? You would say what kind? Is there any different kinds of ellipsoid? Yes, that is what we are coming to. That's why all these many fruits are here. Now, is it like this? Now, I'm taking the largest fruit first. Is it like this? Oh, this is an ellipsoid, kind of an ellipsoid. It's not perfect, so taper slightly on one side. This is what I could get in the market yesterday, the best fit. So this is an ellipsoid, but this is very long. This is longish. I'm not talking about the dimension, but this is longish like this. And Earth is not an ellipsoid like this because Earth is not longish. That is where we come to know about the differences between two ellipsoids. What they are called, I'll show you in the presentation better. I want the secret to remain a little there. But what is the kind of ellipsoid is Earth? Earth is an ellipsoid like this, which means if you see it closely, it is flattened from two ends. You'll say that if you rotate this, it will become like that. No. This is a different kind of an ellipsoid, and the previous one, what I showed you, is a different kind of ellipsoid. We are going to see the difference precisely in the presentation. So these ellipsoids are also called as spheroids, meaning like a sphere, like a circle equivalent to an ellipse. So sphere equivalent to a spheroid. So both these are spheroids, and they have different names. And incidentally, while yesterday I was trying to look at Wikipedia for getting some screenshots, I learned about a third type of spheroid which I was not aware before. So I believe in the principle that when you try to teach something, you need to learn more, and in the process, you yourself learn more. So you can consider this as an important principle. Now that I have some more fruits here, like this is also kind of almost perfect sphere. I'm going to use it for some other purpose. So what do we have? So what we have learned so far is Earth is like a sphere. When you see it from far away, it appears like a sphere, but it is not a perfect sphere. It is an ellipsoid, which is a depressed ellipsoid, and it is depressed at the poles. Why is it depressed at the poles? Because of the centrifugal force. When Earth rotates around itself, there's more centrifugal force at the equator, meaning it rotates with more velocity and the centrifugal force is more. So the mass from the equator gets thrown out and slightly it bulges. It happens with every planet, almost every planet. And I have not shown the picture today. Maybe I'll show it next time. The Saturn is the planet which has the maximum bulge. And I was not aware about it. I was trying to create a two-scale diagram of all the planets, and then I took some screenshot. And I was wondering if I made a mistake. It was not. I could not fit almost a perfect circle around it. It was obviously compressed. So then check the dimension. That Saturn is substantially flattened. So every planet gets flattened because of the centrifugal force. Now then you'll say, but or people used to say earlier that Earth is flat. Even today there are flirters, what they call this, the flat earthers, who claim that the Earth is flat, because for a normal person, when we go along the ground, it's almost flat, and then there's up and down terrain. So Earth is more like a flat thing with a terrain. Where does the curvature come in? So for that, we have always been told in school also, if you want to see the curvature of the Earth, go near the sea. Which means if you go near the sea and see far away, or ship that are coming from far away, you'll see them appearing slowly above the water, which means that there is a curvature there, and a ship which is far away is for you appears below the curvature. That's why you can't see it. So when we go to the sea, then we can make out the curvature. So the first and the most important thing to note here is when we are talking about a curved Earth or an ellipsoidal Earth or a spherical Earth, also nearly spherical Earth, which is ellipsoidal, we are basically talking about the sea level. We are not talking about the terrain which is up and down in the same way, because the terrain is kind of random and it doesn't exactly give a shape. The terrain doesn't determine the shape, but the shape of the earth overall is determined by the water level of the sea. And the terrain is then superimposed on that, and we say that a mountain is so much above mean sea level. When we're talking about levels of any mountains or even depths, we talk with respect to mean sea level. So always we talk about a basic datum. I mean, datum is a technical word which I'm going to introduce later. A basic reference would be the better word. A basic reference, which is the mean sea level. Why do we call mean sea level? Again, the question will be there. What do we mean by mean? Because sea level is not constant. Because of the tides, the sea level goes up and down. So we take the mean, which is the average of lowermost and lowest tide and highest tide, and we call that as the mean sea level. And the mean sea level is practically actually measured and determined at various stations along the coast of entire world. So that is mean sea level. So when we are talking about the terrain, we are talking with respect to mean sea level. So for the overall shape of the earth, we exclude the terrain. So first we have gotten rid of the terrain part, and we are going to discuss about the shape of the earth as a glob of water. If the whole thing was sea, then what is the sea level? So we have already, I've already told you that that this is an ellipsoid, and it is like this fruit, which is a melon. Now, if I tell you that, which I had also done a slight small promo video yesterday and said, if I tell you what if the earth is like a potato, what will you believe it? It is. Meaning this sphere or the ellipsoid of the earth, the water level also goes slightly up and down, slightly, like undulations in a potato. And that's why I also have a potato here. I couldn't get a potato which was nearly spherical, but this shows the feature. See here, here there's a slight depression, then there's a slight rise. Then this side, if you see from side, there's a slight depression. So the shape of the water level or the sea level, actually, when it is actually measured precisely, is like a potato. So the water level is, or the shape of the earth is neither like that nor like that. It's more like a potato. Might not, you may not agree, but we are going to see more demonstrations about it. But 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 this variation is very small. And I'm going to tell you the approximate numbers, then exact numbers we'll see in the demonstration. The variation because of the ellipse, that is the flattening, is of the order of about 500 kilometers. And the variation because of this is of the order of 100 meters. So it's very small. So don't worry, it's not like actually like a potato. But when we describe it precisely, we can call it undulations like a potato. And we are going to learn about them. And then over this shape. Okay, by the way, this shape, that potato-like shape, is called as a geoid. This was an ellipsoid, that was a spheroid or ellipsoid, and then we have the actual shape of the water level of the earth, or sea level, ocean level of the earth, which we have named as geoid, or shape of the geo, which is geoid. Now, when we superimpose the terrain on it, which means the sea depth as well as the mountains, we can call it as another fruit, which I have kept here, which the earth with terrain looks like a jackfruit. So look at it, look at this side. So the terrain would be like this, and it would be up and down, and it will be substantial down. This is more uniform. The actual terrain is much more non-uniform. So we have described the earth shape in terms of different fruits, and That is the best way I could describe it, so that you can understand. Now, by the way, all these things did I gather for this? Actually, I had written a detailed answer on Quora, and that time I thought about all these analogies, and it was written about 2 years ago in Marathi Quora. All these ideas of the different fruits come from me only, but they have been taken from an answer which I wrote about 2 years ago. So today I got a chance to demonstrate. Now we are going to see the presentation. So far, I've just told you the shape. I have not told you about any actual values. I've mentioned some little values. So we are going to actually see the presentation in which we are going to see how much is the variation or what is the variation in the different things. So I will share the screen. Now, this is my presentation. I start the slideshow from here. Oh, it started from start. No, I didn't want that. Sorry. Leave from current slide. Okay. So what is the shape of the Earth? The basic thing, what I had discussed with you without the presentation, if we are coming back here to see some precise photos and some illustrations. So what is the shape of the Earth? It appears like a sphere. And this is incidentally the first photo, or one of the first, meaning I am not saying 100% first, one of the first photos of Earth taken from outside Earth. And it was taken on Apollo 17, about what, 67, maybe 80. So about 40 years ago. This was the photo taken from Apollo 17, and this I have got from NASA's website, not directly, but indirectly through someone. And why is the Earth shown in one corner? Because the person who showed this photo showed precisely like this, but this was the size of the film on which the Earth photo was caught in this corner. When they actually took the photo, that time it was not digital. So on the film, this photo was captured in this corner. So this is actual image of the photo that Apollo 2017 crew captured while going to the moon. They looked back at the Earth because it's not easy to capture Earth photo with completely light. You have the sun has to be behind you and all that. So there are not many photos like this. Before this, all the illustrations that we were making were imaginary. They were not actual photos. And from space, when we go to 100 kilometers, above 100 kilometers, which is called this as the space, we can't see the full Earth. We can see only a small portion of the curvature. So to see the complete Earth, this is also will not be 100% complete. This will be something like, because of that angle, this will be something like, you expect 100% of the Earth would be 50% of the area. This would be something like 49% or 49.9% of the Earth. So as you go distant, you will see more and more. So the Apollo astronauts could go where, since they went that far away, they could take a global picture like this. Now, what is the actual shape? So I'm enlarging this. So since it was, this is how the Earth looks. It is kind of upside down here because this is how the photo was taken, it seems. So I have not changed it. Then they rotated it or whatever. So now this is how we consider the Earth to be. This is an ellipsoid. I have purposely done it, and it is exaggerated. It's not that flat. It is exaggerated. So the same photo I have scaled and made. So this is the ellipsoid that we are talking about, or the spheroid that we are talking about. This is how it is in an exaggerated form. Now let us try to see it in precise dimensions. Whether we can make out the curve, make out the depression and the shape of it. So let me go to the next slide. Sorry, I jumped a few slides. Okay, no, I have not jumped the slides. Before that, I have to talk about the different types of ellipses which I told you. Now, if we take an ellipse, these are the two different types of ellipses which are named here. This one is a prolate ellipse, and this is an oblate, prolate, not ellipse, prolate spheroid, and this is an oblate spheroid. What do you mean by that? So this is an ellipse shape. Now, to get a spheroid or an ellipsoid from an ellipse by revolution, we have to revolve the ellipse shape around an axis, and then we get the shape. So if we revolve this ellipse around the, if we, this horizontal is the major axis or the bigger axis of the ellipse, vertical is the minor axis or the smaller axis of the ellipse. If we take the rotation axis in line with the major axis, then we get a prolate spheroid, which is this. If we take the axis vertical, that is in the direction of the minor axis, then we get the oblate spheroid, which is this. So the name of the spheroid which the Earth's surface approximate is actually a oblate spheroid. So this is again the same illustration. I'm now, for clarity, I'm making it vertical. So this is an ellipse. We rotate the ellipse around the axis, and we get this spheroid, which is prolate spheroid. We rotate the ellipse around this axis, and we get a prolate spheroid. These are highly exaggerated. This is not exactly how Earth is actually, but this is for definition of this different type of spheroids. Now, these, incidentally, I'll tell you one more thing which I learned yesterday. These are called as spheroids because they are generated by rotation. Now, we also have a third type of ellipsoid. In this, what happens is, if you take X, Y, Z axis of the ellipsoid, two dimensions are same, and the third one is different, meaning in this direction, you'll see that the dimension will be same. In the third direction, it is different in this case. So if all the three dimensions are different, then it cannot be generated by revolving, and then it is called as a scalene ellipsoid. Meaning, like we have a scalene triangle, it's also called as a scalene ellipsoid. Really, it's this I just found yesterday on Wikipedia. I wanted to share it so that we have more information than what we already have. So Earth, shape of the Earth looks like this, which is the oblate spheroid. In the original Zoom session that I had, actually I had made some numerical mistakes by adding one more extra digit to the numbers. So I am recording this section again independently. So far we have discussed that our Earth has an ellipsoid shape. We called it whatever kind of spheroid also, name also we have given. Now we are talking about dimensions. So what I'm doing here is to show you the correct dimensions precisely. I have drawn it as a circle, meaning side view of it, you can call, as a circle with the correct dimensions. These dimensions that are shown in meters, if you can easily want to see, you can convert them to kilometers by just considering the commas. So these diameters are about 12,000 kilometers both, but they differ at equatorial and in the polar direction. The polar direction, the diameter is lesser. Equatorial diameter is more. And the difference in the diameters is about 43 kilometers. I'm stressing the word diameter because the difference in radius will be about half of that, which are coming later. So now from this shape, the basic question is, can you make out it's an ellipse? You cannot, because the variation or the change, the difference is so small that from whatever size that we are looking from far away, it looks like a perfect circle, which means it looks like a perfect sphere. Now, to show if we can make out the difference, now I'll add two circles to this. This is not a circle. What you're seeing is not precisely not a circle. It's an ellipse drawn in AutoCAD. I'll add two circles to it. One circle equal to the smaller diameter, one circle equal to the bigger diameter, and give them two different colors. Let us see if we can make out. Now this is what it is. Directly by shape or clear difference you can't make out, but since I've given them different colors, you will be able to see slight different colors of the circle itself, whatever appears to be like a circle itself. Now here, now I have mentioned the radius of the two, uh, the Earth at two places. That is the polar radius and the equatorial radius. This is the equatorial radius. I have marked it here. I should have marked it here. Maybe it's okay. And this is the red one is the polar radius. Now, you can't still see the difference. So what we want to do is let us zoom in. Now, this is the zoomed in version. Once you zoom in, I've zoomed in on that difference. The lower one, what you see is the polar circle, and our upper one, what you see is the bigger, that is equatorial circle, which is shown in green. If I show the previous slide, that equatorial diameter I have marked as green. So I've used two colors, green for equatorial, red for the polar diameter. In this case here, the polar diameter matches with the, since I have taken the top view, the polar diameter also matches with the ellipse. So you can't see three differently, but you are seeing only two. So the difference between the polar circle radius and the equatorial circle radius, now here you can clearly see, is about 21 kilometers. Now this we can see by our eyes only when I've zoomed in 50 times. So that is the most important thing. When we zoom in only sufficiently, only then we can make out the difference. And here in this thing, you can't even make out the curvature. There is a curvature you can make out, but it's very slight curvature. Now, what the scientists have done is they have also calculated theoretically another radius, which they call as the mean radius. Mean radius itself can be calculated in more than one ways, considering a mean sphere, which has an equal area, surface area equal to the surface area of the spheroid, or you can do it by volume. So what this I am showing here, radius of 6371 kilometers, which is considered as the mean radius of the Earth, is actually the volumetric mean radius. That's why I've written here, calculated volumetric mean radius. So with this, mean radius is what most of us use for normal purposes. Now, these are the values are over here. Since in the earlier recording, while I conducted the actual Zoom session, the numbers, I had a mistake. So I had made a mistake. So by chance, if some verbally also some mistake is left, you please ignore it. So these are the correct radius of the Earth at polar and mean and the equatorial radius. So the smaller one here is the polar. Here, this is the mean, and this bigger one is the equatorial. Let me continue with the whatever recording I have already. Now, I talked to you that the shape is like a potato. So this is an exaggerated form of that potato. This is an exaggerated form of that potato, which with colors and with shape. So this shape is made purposely exaggerated to show how that undulations of the geoid are there. So this is the shape of the geoid. Now we have a blue area here below in the Indian Ocean. There the water level would be below than the other places. Here in somewhere in UK, the water level would be higher than other places in terms of from the center of the Earth. Now this is the geoid. This is the geoid shape, which is enhanced. Now it's not. It is also shown in a different map here. It is also shown with again with colors, not with much of exaggeration. So we see this region is blue. This region, UK, is red, Australia is red, which is where the geoid shape. Now, by the way, you'll say that how can we show the colors on the land? This water level model or the geoid model of what ocean sea level is not actual levels, meaning they are actual levels wherever the sea is there, but they are calculated based on satellite information for the entire Earth. They what is called as they measure gravity. So basically, this is what is a gravity potential diagram. They measure potential of the gravity at the different points on the ellipsoid from the satellite, and there are some special missions for that, and they plot it. So when the gravitation is more, there'll be a depression, meaning the water level will go down there. And this entire surface is also called as equipotential surface of for gravity. And though this shape may be slightly undulated, in spite of the undulation, a sphere kept on any position will remain there. It will not roll down or whatever. Though the radius will be down, it will not roll down because the normals, this is a little more technical, because at every point, the direction of gravity will be normal to the surface, normal to the geoid surface. That is the basic principle of the geoid surface. You have this potato-like surface. If there's a slight depression where the direction of the gravity will slightly change, and the direction of the gravitation pull will always be perfectly normal. Normal meaning perpendicular to this geoid surface. So this is how the geoid surface is. Now, it's not only that, it changes over time also. So when they measured it in 1980, it was slightly different. 1984, it was slightly different. 2008, it was slightly different. There are information and models available. So in this animation, what they have done, again taken from NASA Wikipedia, you can, if you concentrate on the Indian Ocean thing, you will see the shape changing. The shape is actually shrinking slightly. So this is the variation in the shape that happens over a period of time, a variation in the geoid shape that happens over a period of time also. Now, this diagram, which I have drawn, simplifies and ultimately concludes the entire shape of the Earth, way we call it. Now, here what I have shown is the mean sphere, meaning if you take it as a perfect sphere only, then I have drawn this line, this black line, because in the other illustrations which I got from, there's a similar illustrations on Wikipedia, but in that sphere line was not shown. I wanted to show it. So this black dotted line which I've shown is a perfect spherical shape. This red line that I've shown is the ellipsoid shape that we call as ellipse or ellipsoid. Now, we also call it as a reference ellipsoid. Why we call it as a reference? Because the geoid shape is measured with respect to this reference. Geoid shape is measured with respect to this reference. So this is a reference ellipsoid. Now, in the previous slide, I think it was there in the previous slide, at some point here, the minimum that the reference goes down is 100 meters. This is in meters. With this dimensions about minus 100 meters here, and this is about plus 80, though it's not shown. That is with respect to the reference ellipsoid, not with the sphere. So we take the reference ellipsoid as the reference, and with respect to that, we plot the geoid shape. And the geoid shape is like this, like a smooth curve. I have 3 minutes left. I'll finish this in this. After this, we take a gap of about 5 minutes. By the time it saves this video recording. And after that, we'll start again. By that time, I'll also clear that doubt of 0, which I have made, most likely made. So this is the geoid shape that you see in a red curved line is the geoid shape. This will be the shape of the ocean level without tides. So you consider no tides or consider the mean sea level everywhere. So that will be the shape of the geoid. And then you superimpose terrain on that. And what is how will be the terrain? So terrain is like this. So this is a mountain. What I'm seeing above the geoid shape is the mountain. This side also above geoid shape, I'm seeing a mountain. This crossing here, somewhere here, what I'm showing is the seashore. There's a seashore here. And this is an island. So there was an interesting question asked on Marathi Quora once, that how do the islands float in water? If you make a hole in the island and through the island up to the water and let the water come out, will the island sink? So sometimes people don't have a clear idea of what an island is. So island is nothing but a peak of a mountain inside the ocean. It will be probably known to most, but to be very, very clear, sometimes it doesn't strike. So everything is a terrain, including the undersea floor is a terrain. Now then up to a certain level, it is filled by water, which is the geoid shape. And the mountains which are below in the ocean, whenever the peak of those mountains come up, it becomes an island for us. So this is the shape of the entire thing. I've shown also ocean floor here. So you have ocean floor, terrain, the mean sphere, island, and this is the geoid. So we have completed the discussion about the shape of the Earth. In the next session, we are going to talk about the latitude, longitude. Now, if you have a quick question, you can ask so that I can answer it in the. Anyone who wants to ask a question can unmute himself and ask. There's 1 minute left. Answer will be given mostly in the second session. So, where do we go now? So, what we have done so far is we have talked about the shape of the Earth. We have decided that it is an ellipse. It is approximately an ellipsoid, meaning it is also approximately a sphere, but more precisely an ellipsoid and more precisely a geoid. Now, the next thing is how to measure or how to make actual maps. The first thing that we have to talk about is latitude and longitude. Sorry. The first thing that we have to talk about latitude and longitude. Now, how do almost all of you know latitudes and longitudes exist and how they are? The cat is making me move here and there. The cat had come in this room and was refusing to go out, and now after some time he wanted to go out. This is what happens. Okay, so how do we start with latitude, longitude? What is latitude? What is longitude? So what is the basis? Are they arbitrarily decided, or there's some precise rules for it? How do we decide that? The basis for any planet or any even star, you can have latitude, longitude even for a star, latitude, longitude even for sun, for moon, anything. Is its rotation around itself. Almost every spherical object in the universe rotates around itself, and now that rotation around itself is called as the axis of rotation. In case of Earth, that axis is north south, which is actually for every object it is north south, because that is how we define north. The axis of the rotation gets defined first, meaning it is natural, not defined by anyone. So whatever is the axis of rotation, we decide that that is the north direction. Now this is naturally decided. It exists naturally. So we don't have to decide. Now, when the axis is there, we take a plane perpendicular to the axis at the center, passing through the center of the planet, and we call that as the equator. So axis, north axis, a plane perpendicular to that north axis passing through the center is the equatorial plane, and the line of it, which is cross section of that plane on the surface of the Earth, is the equator. So the north direction, north pole, south pole, and the equator get defined naturally. Once that is defined, if we want to measure the coordinates on the Earth, so we need to have another coordinate. I mean, if we are measuring only on the surface of the Earth, so we need only two coordinates. Another coordinate. The best way is to have it. The best way is to have it perpendicular to the first one. Now, perpendicular to latitude, if we draw a line, it is the longitude. Now, so we have equal. Once I've defined the equator, I said. So we have from equator we take degrees. Equator considered as 0. Then we have degrees on in the north direction from 0 to 90, in the south direction from 0 to 90, and we define the latitudes, different latitudes, which are parallel to each other. Parallel, very important. Now, the longitudes go right angles to that from North Pole to South Pole. Every longitude goes from North Pole to South Pole, and they are not parallel. They are not parallel to each other, but they are perpendicular to the latitudes. All of them are perpendicular to the latitudes, but not parallel to each other. Meaning they are locally parallel, but they'll ultimately meet at the North Pole and at the South Pole. So they're actually not parallel, etc. So we have longitudes. Longitudes will go for 360 degree. They'll from 0 to 360 or 0 to minus 180 or 0 to 180, whatever way you call it. Now the question is, where is the zero longitude? Now, as I said, latitude is decided naturally. The equator is decided naturally. Longitude is not decided naturally. Meaning, there's no natural reason that you have to have a longitude at a particular place. Zero longitude should be at a particular place. Now, because of that, in earlier ancient India, the zero longitude was taken as a longitude passing through Ujjain. And other countries would have taken longitudes from their own countries or their own measurements. The same way, Britain decided that the English astronomers decided that they will have the longitude 0 at an observatory which is in Greenwich near London. So that's why we call it that Greenwich as the zero longitude, and that's why we call that the zero time at that as the Greenwich Mean Time. So the longitude 0 is arbitrarily decided by humans. Equator is decided by nature. North Pole is decided by nature. Zero longitude is decided by humans. Okay. Now, so once we know now clearly that this is how longitude and longitudes are defined, we have to come to the next concept, what is called as the datum. Now, when I said that the longitude 0 is decided arbitrarily, this is also, that arbitrary decision is also part of a datum. Meaning, what is a datum? Now, we have the entire Earth, on which if I ask you that what is the coordinate of your city, Bangalore has this latitude and this longitude as the coordinate. Delhi has this latitude, this longitude as the coordinate. So these are all latitude longitudes which are precisely defined. And nowadays with GPS and mobile phone, we can precisely say that this is my precise longitude, latitude where I'm actually standing. So GPS can give you a measurement within plus or minus 3 meters also. So which is very small. 1 degree of, by the way, 1 degree of latitude or longitude at the equator is equal to about 110 kilometers. At the equator, 1 degree is equal to 110 kilometers. So now you can understand 3 meters is a very small degree, whatever. I'm not remembering that number. So the GPS gives you a very high precision and can tell you the precise latitude, longitude of your location. Even earlier map makers and surveyors, by doing survey, they would decide precise latitude, longitude locations of different places. So the precise latitude and longitude of a particular place, my place, is decided by what? It is decided by the datum, because since I can have a zero longitude, which is any place. If I take my latitude longitude with respect to Ujjain as the zero, then our latitude will not be our latitude will be somewhere near zero, meaning or 1 degree, 2 degree, 5 degrees, whatever, not like 75 or 80 degrees or whatever we have. So your precise location of latitude, longitude of any location is decided by the datum. Where is the precise location of the zero of the longitude and the precise location of the equator? And then it is also decided by the shape, geoid, to get it precisely. Based on the geoid shape, your latitude, longitude will slightly change with respect to what was measured hundreds of years ago by just measuring surface distances. Now, I'm referring to the same thing, equator and latitude are arbitrary, zero longitude is arbitrary. So because we can have multiple longitude or multiple possibilities of zero longitude, we can have more than one datums. And for precision of maps, for centuries, there have been different people have used different datums, which I already told you, and they are named differently. Now, the currently used popular datum is what is called as WGS 84, which the term many of you might have heard. Let me not go to that, because before this I want to show you a presentation or something else. So WGS 84 is the term that is used for the datum that is currently in use. Why is it popular? Because WGS 84 was been precisely measured in the and frozen in the year 1984, and after that the GPS system came somewhere near that or after that. So the current GPS system started using WGS 84 is the as the standard, and with respect to that datum, it is telling you the latitude and longitude of every place. So even though advances have happened after that, the shape of geode they're updating every 10 years or whatever. So there's a geode of 2008, there is some other geode of 1996 or something. So advancements have happened after 1984, but WGS 84 is the standard that is commonly used because it is used by the GPS system. Now you'll ask me, if this is the standard, is there anything special about it, or is there meaning when I said that your precise latitude and longitude is decided by the datum, does it change? Was it different in the past? Or if I don't measure it precisely, will it be different? In the map, was it different? Does GPS tell me a different latitude longitude? The answer is actually yes. WGS 84 is different slightly from the previous systems that were in use. And once we change the datum, the precise latitude, precise word is very important, precise latitude, longitude of different places changes. How it changes, I'll actually show you the demonstration using Google Earth. Okay, what I've done here is I have made some marks on the Google Earth already, and I have called them as datum. Let me zoom into this datum directly. Or it is not zooming from there. Okay. So what we have here is the Royal Observatory of Greenwich in the on Google Earth. We are seeing that place. Now this is, if I zoom out, this is London. This is the famous River Thames. Now we have on the banks somewhere, we have the Royal Greenwich Observatory. Now, there were other photos from which I have determined that this is the line which is marked in that Greenwich Observatory as the prime meridian. There's some copper marking here also. Maybe I can't see from here, but I've seen other photos. You can Google and see other photos. I think there's a copper plate here in this line. So this is the line which is the prime meridian, or it should be ideally zero longitude, or it was the zero longitude when they decided on Greenwich as the prime meridian. And they marked a line precisely to mark that. Now in Google Earth, I can check the longitude of this. I'll click on this and I'll say get info. Now the what I'm seeing here, if you see here, is its latitude can be whatever, but its longitude is not precisely zero. Its longitude is 0 degree and 0 degree, 0 minutes, 5.29 seconds west. How this has happened? This has happened because after this, after Greenwich line meridian was decided, more recently in 1984, we decided to have a different datum. Why did we try to shift the meridian itself? Most likely because of the new measurements that were done of geode, new measurements that were done. The best fit that they could get without disturbing other continents or other coastlines and other things. For that, they had to shift the meridian itself, shift the precise location of the meridian itself. Otherwise, if they didn't shift this, probably the coastlines and other things, more features would have shifted rather than shifting this to keep the maps similar. So where is the zero? It is about 100 meters away. It is here. I have marked this point, which is the same latitude but zero longitude. I'll click on it and show you the info. This, it is zero longitude, 0, 0, 0, 0. Now let us measure the distance between the two. There's a, it's, one moment. Okay. I'm using the scale here. I set it to meters, and I'll measure the distance from here to here approximately. Now this is about 100 and I moved it a little more. Okay. This is about 101 meters as we can see here. So instead of telling examples of different datums, I wanted to show you exactly practically how the WGS84 datum is different from the earlier datums. It is a shift of about 100 meters. And because of that, the current precise zero longitude is not precisely at the prime meridian, which was marked at Greenwich, but about 100 meters to the east. You might say 100 meters is not too much, but it matters these days when we are using driving directions and Google, Uber, and everything. If there's a parallel road which is 100 meters away, it can give you an error. So in GPS, 100 meters is important. In surveys, 100 meters is substantially large. There are surveying instruments nowadays which can be as accurate as centimeters. Your handheld GPS that we use in smartphone is accurate to the extent at about 3 to 5 meters. Uh, there are special handheld GPS devices also which are accurate that, and there are special survey class devices, GPS devices, which are precise to a few centimeters. So now we have, I have told you what is the datum. Now, why are we talking about this? Because datum is the basis of the entire GIS, meaning the datum is the basis of entire GIS about how and where, which latitude, which longitude is there. And now, why I'm stressing on this datum, and I've spent some time on this, is afterwards when this I had given one talk also in one place once, and I stressed it. Many people are not aware about the difference between datum and projection. They confuse between the two. I have not yet told you what is a projection. So they combine the two together. Datum is different, and projection is something different for making maps. That when the two combine together, we use for making a map, but they are different. So why are they different, and how we make maps? That we are going to discuss in the next slide. So what is a good map? Meaning, if you want to make a map of, say, my city or my place, it's easy. Meaning, I just do a survey, uh, take measurements, make a tape, precisely measure the thing using surveying instruments. I make a precise survey, and I make a map. I make a map on a plain paper, and it works. It's good enough, but it's not good enough for large maps, because for a small map of a city or a plot or for that matter, or a house, even even a small district. If you make a flat map on plain paper by doing some surveying, it may not be as inaccurate, because there's not within that much distance. There's not much of curvature. It doesn't curve as much. So, what is a good map of Earth? How do we make a good map of Earth? A flat good map of Earth. The only way to make a perfectly good map of Earth is to use a globe. You cannot make a perfectly good map of Earth on a flat paper. Why? Because the Earth is spherical. Now, this is the sphere which I have. Now, if I want to convert this sphere into a plane map, how do I do it? I have to tear it and then stretch it. So the moment you stretch, the shape changes, the distances change, and there is a distortion. So when I say a perfect map, a perfect distortion-free map, that is what I'll say. If you want to make a perfect distortion-free map of Earth, you have to make it only on globe. So the only best way to have a perfect distortion-free map is a globe. A flat map is never accurate. Now, what do you mean by a flat map? So, if you want to show the entire Earth on a flat surface, which I've already shown you in previous sessions, in a rectangle, I had to do some changes, or I had to stretch them. How did I stretch them? As I showed you previously, that the Greenland became much larger. and some other Antarctica continent became much larger, and the things got distorted. Now, if we don't want a distortion, then how do we do? We can't do anything. But to keep the distortion to minimum, what we can do is we can tear the Earth apart in a certain manner. Now, this is what I am trying to do now. See here. I am trying to make a flat map of the Earth's surface by peeling this orange. This is not orange, this is Mozambique, in one piece. Now, actually, I wanted to do it before this, but now that I'm doing in front of the camera, I'll stop sharing so that you'll see what I'm doing. I am trying to peel this orange so that I get a one piece map of the earth, which is orange shape on my screen. And then we call that as the projected map. It is a flattened map. I'm trying to do it as best as I can, which I have done it many times before. But today, instead of doing it before, I thought that I'll demonstrate making the simplest projection flat map, which may not be useful, but it's the simplest one to explain. So I have succeeded. So what I have here is I have a kind of a flattened Earth. Now this I can put on a flat surface and it will be nearly flat, not perfectly. It has to be distorted. As I said, there is no way you can make a map perfectly flat without distortion. But this is a very easy and good way to demonstrate projection, which I've almost always doing. I've given a few talk at different places about projections and maps. Every time I use this. Now, if I flatten this, tomorrow I'll show you a photo because I don't have a ready-made photo since I did it right now. If I flatten this, this is how it will look. And there are even earth maps which are made like this, not this shape, but cutting it in different suitable positions, which are called as interrupted projections. That the term for that is interrupted projection. So what we have now is how do we make a flat map? So what I was coming to is the ideal way for a map to be made is on a sphere without any distortion. But a sphere map will not be practically sphere map, though it is perfect. It's not practicable because if I have to show 100 maps, then I have to carry 100 spheres for the entire Earth, which is not practically possible. So if I have to make 100 maps in a book, I need them to be flat. So for that, we use what is called as projections. Now, in detail about projections, a little depth I'll cover in the next session on next Sunday. But today I will explain to you what is a projection in general. Now, I don't know about among the participants how many are engineers or whatever, but everyone who's an engineer who's taught engineering drawing is taught what is a projection. What is a projection is, suppose if I want to draw, now let me take this shape itself. If I want to draw or make a drawing of this, how do I do? A precise drawing. An artist will keep it at a distance and draw how he sees it. It's very important. Artists will keep it at some distance, and from that distance, he'll take that measurement. They use a pencil like this, meaning artists use a pencil like this at a particular distance and take measurements like this. We used to do this in school, what they call it as the object art. Meaning, in Marathi, they used to call it Vastu Chitra. They used to keep some objects in front of us and ask us to draw that. And then we used to do measurements like this. So an artist will do like that. Meaning they take measurements and transfer them on paper and draw it. Now, this is not precise because the artist is seeing from his eye point of view and is seeing it at a particular angle. Hence, what he gets is what they call in architecture as a perspective projection, meaning it is not precise. Meaning, as if you've seen a perspective projection, the parallel sides of the buildings would meet at a point. That is a perspective projection. I'm talking about general projections in general and specifically to engineering. So perspective projections are not precise projection where you can do dimension. So what we do is what is called as normally orthographic projection. We take this object. Now suppose this is the object. Then on top of the object, let me take a paper. On top of the object, what I do is I place a paper. Or between the object and me, I place a paper like this. I place a paper like this. Now from every point on the object, I draw a line perpendicular to this paper. Meaning I take every point on this object and draw a line perpendicular to the paper. Paper is flat and I'm drawing a perpendicular line to the paper from every point. And wherever it intersects that paper, intersects the paper, I'll mark that point as that feature. Meaning, so this top point will get marked as a at a particular point on paper. This bottom point will get marked as a particular point on paper. So when I keep a paper like this precisely and draw a project, make lines perpendicular to the paper, it is called as a parallel projection. Again, here people will make people could make confusion between orthographic and parallel. This is a parallel projection, meaning I take parallel lines, all lines parallel, which are all perpendicular to this paper. Now, I take one view or one projection from this direction, which is a parallel projection. Then I take another projection from an inner direction, which is 90 degrees to that. And now we have two projections. Then I take a third projection in a direction which is 90 degrees to that. Now I have three projections with the paper at 90 degrees to each other. This set of three projections is called as an orthographic projections. Now, for the sake of clarity and for understanding for some of you, I've explained that also. So we take a parallel measurement, parallel rays coming from an object to the paper and draw a projection, which is a two scale precise drawing of that object. Now we take a set of parallel projections at 90 degrees to each other. They're orthographic projections. Now what is a perspective projection? Perspective projection is used like this. In that case, I don't take lines that are perpendicular to the paper. What I do is now I'll show you from other side. I have this object here. I keep a paper in between me and the object, and I stand at a distance. Now what I do is instead of drawing lines from each feature on the object perpendicular to the paper, I draw a line from my eye to each feature on this object. So the lines are not parallel. Every line on this object goes from my eye to that object. So what I'm doing is how I see a building is drawn using a perspective projection. A perspective projection is when you keep a paper in between you and the object and draw lines, not parallel, but each and every line precisely meeting your eye, which is at a point, meaning your eye point, your iris, if you want to be precise. You draw a line from your eye, my eye, through the paper, going to the object, and wherever it intersects the paper, at that point on the paper, I will draw that point of the object. So when I draw like this, I will get what is a perspective projection. I've explained to you in brief. Now, these are the projections which are used in engineering. Now, in geography, we use similar kind of projections, not exactly same, similar kind of projection. What we do from the earth or from this feature of the earth, we project lines. We project lines so that they intersect a paper. Principle is same. From the sphere, each feature of the sphere, we take a point and we make it intersect a paper. Now, what is the paper? Where is the paper kept? Again, similar way. If I keep a paper flat like this and make parallel lines which go through like this, I will get a projection of the map, but I'll get only half the globe because from one side I can only see half parallelly. Or if I draw the other side, then they'll get superimposed, so they'll have no meaning. So if I take a projection like this, I'll get a projection, which is what I showed you in the previous session, Earth as seen from space, which is what we are seeing right now on this share screen of this globe. What you are actually seeing, meaning the globe, actual globe is a spherical, which is not a projection. But this is a photo of the globe. So in the photo of the globe, what you are seeing is precisely this, is precisely what you will get this projection, which is called as the orthographic projection. Now in GIS, this we call as orthographic, we don't call it parallel. Now the terminology in engineering, some people confuse that orthographic projection only when we make 2 or 3 sets of projection, which are then called as orthographic, but each of them has to be a parallel projection. Now same way, in GIS, the globe that you are seeing in front on the screen is an orthographic projection of the Earth because it is flat. This is not actual globe, this is a photo of the globe. So this is the simplest and the first projection. Rather than telling you some other projections, I'll tell you the simplest projection first, which is what you see here. Whatever globe you are seeing. Now, what is happening in this? How accurate is this? Whatever I am seeing in the center of the globe. Okay, now let me show an actual globe. Now I'll stop the sharing of the screen. Okay. Now I have an actual globe, which is very small. I'd say it's tiny. Now this is the actual globe. Now, from when you look at the globe, what you are seeing on the screen is an orthographic projection of the globe. Since it was a mirror image, I couldn't make out India. So this is the orthographic projection, what we are seeing of the globe. Now try to observe how accurate is this. Whatever is near to the center, right in the center, is good enough, meaning it is proportionate. But everything in the edges gets heavily distorted. It gets compressed, it gets heavily distorted, and it's not seen properly. So this projection is good enough for what? It is good enough for showing a small area only in the center of the projection. And at the edges, they are only for reference, that they're not for precise work. So orthographic projection is also used. This kind of projection is also used when we want to show a small area, especially a country on the globe. And if you still want to see the entire globe in the relation of the entire globe, how it looks. So this is the best example. Now, precisely and in detail, we are going to learn about projections, or more different type of projection later on next Sunday. And we have about 2 minutes left. You can shoot out any questions if you have. If you don't have, you can also communicate with me from whatever means you have got to and know about this. You can write on Facebook or write on YouTube. I'll pause here. Anything to ask? Huh.
Hello, good morning, sir. I just wanted to ask, like, just like they decided zero meridian, dateline also was decided like that, or was it some geographical thing?
Dateline was basically decided in a way that it doesn't cross a continent. It has to be opposite to zero meridian. That was obvious. And the precise dateline could not be straight, because if you make it just 180-degree, it would cross the meridian. It would cross the continent, some portion of the continent. So once it crosses the continent, then you'll have one day on one side of the continent, other than the other side of the continent. So it was based in a manner, zigzag manner, such that it doesn't cross any continent. Now this datum, meaning the datum change, would have brought in some change about 100 meters on the dateline. So I don't think 100 meters will matter much, because I guess